All right, let's get started. So I'm assuming linear transformations have been covered in the last session, and most of week 5 actually has been covered in the last session, right?
Yes, sir.
Yes, sir.
Yeah. I think only linear isomorphisms and uh, basis, how basis determines linear transformation, that is remaining. So it'll be a bit of both the remaining topics from week 5 and some of the topics from week 6, maybe even all of the topics of week 6, depending on how fast we go. So before we get into the definition of a linear isomorphism, I'll give you a little bit of the big picture. It's some sort of a zoomed out high level overview, which is not very important for the course as it is, but it just because it is very easy to get lost in symbols sometimes. We have been seeing a lot of things, matrices, systems of equations, now vector spaces, then linear transformations. So what is happening and where we are? I'll just give a sketch of that. It'll be a little bit abstract, but whatever you understand is enough. This is not very important. Whatever in the first thing, it'll just clarify some of the things, hopefully, for you guys. So whenever something is introduced in mathematics or something is taught, there is some uh, common structure. So first, you learn the definition of an object. Of a mathematical object, I'll just say an object. In this case, you learned what vector spaces are, right? In our particular case, it was this thing where you had a set along with two operations which satisfy certain conditions. And then what you typically do is look at examples. You understand a definition not using abstract symbols, but by working with explicit examples, examples and non-examples, what trivial examples are, what non-trivial examples are, and when does some structure fail to be the given object, when it fails to fall into the class of the given object, in this case, vector spaces. We have seen lots of examples of vector spaces and non-examples of vector spaces. And then typically one would go about constructing examples. Is there a way to manufacture examples? In this case, and two substeps are subclasses. Like whatever object you see, in this case, a vector space. So we saw what a subspace is. So within a vector space, you can have substructures which fall into the same class. And again, there are subspaces, there are subsets which are not subspaces. Again, you go into the same examples, non-examples thing. And then there are other constructions. I won't specify what they are. Even for vector spaces, there is something like direct product and all that, but that will not go into. One thing that we have seen is subspaces. And then you look at equivalence of objects. Now, what is equivalence of objects? In the context of just sets, for example, when do you say one set is the same as another set? That is when there is a bijection between those two things. That is a 1-1 and onto mapping. What does a 1-1 and onto mapping? I hope you guys know what a 1-1 and onto mapping is. So if I have, let's say, two sets A and B, and there is, when do I say that there is a bijection between them? Suppose I have a map between them, which is given by F. So what is a bijection?
So you can create a function where you have ability to go from one set to another and come back without, you know, it's like unique
Yes,
one-to-one mapping.
correct. So the two things that you need to check are 1-1 and onto. So what does 1-1 say? So what is a function? A function associates to every element in A, it associates a unique element over here. So it could be this, this, this. So of course, for every element in A, there is an element in B. There is a unique element in B, which is called f of A. So what does B is equal to f of A implies A is mapped to B. And for every A, you need an f of A. That is what a function means. Like inputs, all of the inputs should have a unique output. But what a function, a general function does not need to satisfy is that different inputs need to go to different outputs. For example, in this case, let me call this A1, A2, A3, A4. It's just a 4-element set to a 3-element set B1, B2, B3. Let's just look at this function. Right. Okay. A4 I've not assigned to anything. I'll just assign it to B1 itself. Now every element in A is mapped to an element in B, but there are multiple elements mapped to the same element, right? So this is satisfied. For every A in A, there is a unique B in B mapped to it. So in this case, the rule of the mapping is f of A1 is B1, f of A2 is B3, which is the same as f of A3, and this is the same as f of A4, right? F of A4 and f of A1 both are B1, and f of A2 and f of A3 both are B3. So for every A, there is a unique B in B is fine. But we also see that every B in B does not have a pre-image. I'll use this term pre-image. I don't know if this is the exact terminology that has been used in this math course or the previous math courses. But pre-image just means an element in A which is mapped to this guy. So which element does not have a pre-image in this particular example?
B2. B2.
B2, right? And also, elements in A how do I write this better? Pre-images are not unique. I'll just write it in this way. Pre-images are not unique. Meaning, for example, B1 has two pre-images, A1 and A4. So this is not like a one-to-one correspondence. So one of the comments that was said earlier is there should be a way to go to one set and come back, right? So if I go from A1 to B1, I can come back to A in two ways because B1 has two pre-images. So that is one obstruction. And there has to be a way to go to every point of B. And there is no way to get to B2. So in that sense, this is not a bijection and it fails both conditions 1, 1 and onto. So this thing is called onto or surjectivity. And this thing is called 1, 1 or injectivity. These are the conditions that fail. So if every B has a pre-image, then the function is called onto. And if every pre-image is unique, then it is called 1, 1. So this is, of course, something you've already seen. I'm just giving this as a revision. But then coming back to the big picture, we call this an equivalence of the object. So just for set theory, we call a bijection an equivalence, because this gives us a way to go back and forth. Whatever I do on A, I can just do it on B. In some sense, the elements in A and B are just different names for the same sort of structure. So far we have seen for vector spaces what the definition is, the examples, non-examples, and constructing examples using subspaces, and some special examples like homogeneous system equations and so on. But what is the notion of equivalence of two vector spaces? This is what we want to see. So whenever you have a set with some additional structure, what is the additional structure that we have over here? We have these two operations, right? So I want that operation also to be doable in either set A or set B. Like if I'm taking two vector spaces V1 and V2, whether I do the operations in V1 or whether I do the operations in V2, it should not make a difference. If that is the case, then I say these two vector spaces are the same. So now coming back to the course content, this is where the story ends and actual content of the course begins. This is a definition you've probably already seen. Given vector spaces V and W. Of course, V and W come with their own plus and dot. This we will omit just for convenience so that it does not become notationally heavy. A map T I think is the standard notation for linear transformations, is if 1 T of V1 plus V2 is equal to T of V1 plus T of V2 and T of CV1. I won't write C dot V, I'll just write CV. It is understood where things are happening. This has to happen for all V1, V2, V in V and C in R. So this is a formal definition, but what exactly is happening? So one thing to note is this plus is in V and this plus is in W. We use the same plus, but very strictly speaking, this is the plus of V and that's the plus of W. Similarly, this is the scalar multiplication in V and this is the scalar multiplication in W. So if you're using some non-standard additions or scalar multiplication, you should be careful about that. So what this definition is saying is that the operations are respected even across the maps. So if I have two vector spaces, V and W, this may not be the best way to represent vector spaces. They seem sort of bounded, but they can never be bounded. But just think of it as a representative diagram. So if I have two vectors, there might be more. I'm just taking two particular vectors and I'm looking at their images, right? W1, W2. If I do a V1 plus V2 over here, I'll get some element V1 plus V2 in this thing. And then if I look at this guy goes to some W. Yeah. So if I do V1 plus V2 and then take the image under T, this map is T. That is the same as taking the image of V1 and V2, which are W, and then adding. So if I add first and then take the image, it is the same as you take the image first and then add. So this is taking the image first and then adding, while this is adding first in V and then taking the image. So in that sense, the vector space operation is respected with respect to the map. So adding and taking image is the same as taking image and adding. Similarly, the other operation that you are having when you talk about a vector space is scalar multiplication. So if you take a vector v, I'm not going to do the same thing again. I'm not going to draw the image again. But if you have a vector v, you scale it and then take the image. It is the same as taking the image and then scale. So linear transformations are the natural class of maps in the universe of vector spaces, in the sense that they tell you that it is okay to do it over here and then take the image, or you take the image and then do it in the target map or the range map. Is there a doubt?
So I just wanted to, just take a real life example so it will become clear, right? So let's say we create a linear map where the input is
Yes.
the weight of a person on Earth. The output is if the astronaut goes to moon and does the weighing there, right? So we know that moon's gravitational force is 1/6 of Earth. So if my weight is, let's say,
Yeah. So
60
it
kg here, it's 10 there.
yes.
So whether we
Yes.
take the summation of two people's weighing together in Earth, and if I do transform that, it's equivalent of weighing these people on moon and then adding them together. That's basically kind of something, an
Yes.
example of one-to-one mapping, so that way we'll be able to
Yes.
relate.
Yes.
It's sort
Yes.
of abstract.
Yeah, that's correct. And in this case, it is just by six. So that's a very simple example. You can probably take some of those grocery shopping examples that the prof has given in the videos, which is also another demonstration of the same thing. So it's like if you double the input, then of course the cost of your groceries will double. So that is a linear thing. And non-linear, you could take something with exponential growth, like compound interest with respect to time, the profit you get with respect to time. That is one classical example of non-linear. So this thing actually says that if you double your input, your output will be double. So, and if you add, and that the example that you give is of course a real life example of that. In that case, it is just scaling, and in R to R, you will have only things like scaling. So yeah, this is the definition of a linear transformation, and I think this has already been discussed. Now, if I have a linear transformation between two vector spaces, that does not imply that the two spaces are equivalent, because we have made sure that plus and dot, the operations of the set, behave well with respect to the map. But what we have not done is the first step itself. I want all of these things. A vector space is defined by three things. And across a map, I want all of these three things to be respected, or I want them to behave well. So I've taken care of this, I've taken care of this. So when do I say that a set is the same as another set? That is just using bijection, which is one and onto. So which brings us to the next part of the definition, a linear transformation. I'll just write a bijective linear transformation. A linear transformation which is also bijection. Is called an isomorphism. Like linear isomorphism is what is the precise term. So what do you have when you have a linear isomorphism? If you have two vector spaces, once again, I'll just denote them like this. Whatever you do in V can be equivalently done in W. This is what it says. So if I have two vectors over here, I have unique two vectors over here. As in V1 and V2, if they are different, then W1 and W2 will be different. So if I do V1 plus V2, it is the same as doing W1 plus W2 in the sense that I can look at what V1 goes to, I can look at what V2 goes to. There I'll get W1 and W2, and then I add them, get W, and come back to this thing. So this coming back is facilitated by the bijection, right? Otherwise, not every element needs to have a pre-image, so it may not be able to come back. Or even if it is able to come back, there is no guarantee that you will come back to a unique guy. There might be multiple pre-images of the same vector in your target. So since you can go back and forth, which is facilitated by the bijection, and since the operations it does not make a difference where you perform the operations, this is the best notion of what sameness is in vector spaces. So I don't know how many of you have seen the discourse post by Mr. Bhaskaran. So he had asked, is R2 a subspace of R3? So what is the guess? What is the answer?
Yes.
Any other answers, or does
Yeah,
everyone agree that it is true?
yeah, it should be.
Um,
So when do
zero.
you say something? Wait. Yeah, go ahead, please.
Yeah. So zero. The zero of this R2 exists in R3, and it is
Okay, R2
closed under addition.
is just this, right?
Uh,
I think
And
that
R3
R square, maybe the question is R square is a valid, vector space. RQ is a valid vector space. Is R square a subspace? That's, I think, the main
Yeah,
question.
that's what I'm asking. Yeah.
Yeah.
Is
but
R3 a
yeah,
subs
it
R2 a,
can be. But if just we put Z zero.
Uh, can I comment on this, sir?
yes.
I discussed with Bhaskaran sir on this, sir. Maybe my argument was R2 cannot be a subset of R3 because the elements in R2 is not the same element as is present in R3. Z component is
Right.
missing over
Right. So this is actually not even a subset. Right. So then how can you say that this is a subspace? So very strictly speaking, R2 is not a subspace of R3 because it's not even a subset of R3. But then if you look at the following map from, let me call this WXY, which is XY0. So I know this is a subset of R3, right? I just forget about what the third coordinate is. And look at the map which takes, well, in this case, the elements are of the form XY0. So I'll just take it to XY. Is this a 1-1 map? Is
Yes.
this a linear map? Is this an onto map? There are three questions, right? Let me call this guy as F. You can check that F is 1-1. F is onto, and F is a linear transformation. These are three things that you have to check.
It is isomorphic, I
Is
think.
there a doubt?
No, I'm answering.
Okay, these three things are fine.
Yes, it will be one on
Yeah.
transformation.
Yeah. How do you check one-oneness? One-oneness is just if I have two things
The function of them
in
will
the
be
target space.
different.
Yeah. Typically, how you check it is if f of, let's say, x is equal to f of y, this should imply that x is equal to y. You cannot have different x and y going to the same thing. So in this case, if you look at two things, f of x1, y1, 0, if this is equal to f of x2, y2, 0, then this would mean that x1, y1 is equal to x2, y2. And just by comparing coordinates, I can just go back to this, x2, y2. And this is 1, 1. Similarly, you can to check something is onto, you have to take any element in the target space. In this case, it is R2. And you have to manufacture a pre-image. You take any xy, you can always look at the element xy0 in wxy. Of course, that's a pre-image for R2. And f is a linear transformation is easy to check. If you take x1, y1, 0 plus x2, y2, 0, and you check whether f of x1 plus y1, x1 plus x2, y1 plus y2, 0 is the same as, it's a routine check. So I'll just leave this as exercise. But what does this say? All of these three things are true. So f is an isomorphism. So R2 as it is not a subset of R3, but there is a copy of R2. Like there is when you say something is isomorphic to something else, that means it is a copy of that. It is just the same vector space with different names. That's all. So there is a copy of R2 as a which sits as a subspace of R3. XY plane was just one choice. You can take any plane which which in other words is any subspace of dimension 2 fit to R2. So in that sense, this question of is R2 a subspace of R3 is slightly nuanced. Typically, once isomorphism, is there a problem?
Yes, sir, there was a little.
There's no problem.
Oh,
Continue. It's okay. It's okay. Continue.
Yeah. Okay. So whenever you declare what isomorphism is in a class of objects, in this case vector spaces, you sometimes just say, is this, when you say, is this property satisfied by something, you can have isomorphic copies and that works. So, and up to isomorphism, this extra word is not used. So is R2 a subspace of R3? If it is read as, does there exist an isomorphic copy of R2, which is a subspace of R3? Then the answer is yes. But is R2 a subspace of R3? It is not true for a very simple reason that R2 is not a subset of R3. So there are two coordinates here, there are three coordinates here. So
Sir, x comma y in R3, is it wrong to think that it's already implied that z is equals to 0?
yes, it is. Why would you, why is this not a point in R3?
It
So
is,
there's
but
this
since
whole
it's not
plane.
available,
If it is not available, it's like 0 is just a choice that you are making because uh, it has some special properties being the identity and all that in the respective domain. But 0 is not any different from any other letter. If you
okay,
look at the
yeah,
elements as letters.
fair.
So uh, xy is, and looking at xy as xy0 is actually some isomorphism that is happening in your mind.
Mm-hmm.
So this is why formalizing isomorphism and understanding them as something that you already know is a good exercise to do. So that is precisely what's happening, that when you say xy is xy0, then you're actually doing some sort of mapping in your mind which looks like this.
Yeah, yeah.
And you want to do 0 for one obvious reason, that you want 0, 0, 0 to be in your space. but still there is no canonical choice. This is why I said canonical choice. If you take any plane through the origin, you can always find an isomorphism that we'll see soon. So next example is, let's take specific numbers. Does there exist an isomorphism? Now onwards, I'll not say linear isomorphism, but isomorphism will always mean linear isomorphism.
Sir, uh, hello.
Yes, go ahead.
So if you take the coordinate x comma y comma let's say 2, will it have
Okay.
an isomorphism in R2?
So if you take, okay, I'll try to finish it in this box. Otherwise, I'll take it up later. So you are saying take W as x comma y comma 2. Is this what you're saying?
Yes, sir.
So this is not a vector subspace with the usual addition and multiplication. So you cannot talk about this being isomorphic to some other vector space. So, but if you redefine your multiplication as xy2 plus say x prime y prime 2, your elements are of this form, right? So what is their sum? If you call it x plus x prime y plus y prime 2 itself. Like I'm just keeping that symbol as it is. That's why I said 0 is just a symbol. It's just one of the candidates. So this will actually, and scalar multiplication again, if you say c times xy2 is equal to cx, cy, and 2. I don't really do anything to that 2. So that my operations are closed under addition and scalar multiplication. And this forms a vector space. You can check that this definition of plus and scalar multiplication actually makes it a vector space. And this is the same as R2. This is isomorphic to
Okay.
R2.
So basically, we are changing the definition as per our requirement.
Uh, yeah, in some sense, if you want this to be a vector space, this is one way to do it. There might be other ways you can define a vector space structure, but it will always be isomorphic to R2 is what I'm claiming. That is not very obvious right now, as in why would any vector space structure be an isomorphic copy of? You can take this as an exercise. You can check that this thing inside the box is a vector space and it is isomorphic to uh, R2. This is one thing that works. And using the usual addition and multiplication coordinate wise, you can see that this is not a vector space because it is not even closed under addition. If you take xy2 and x prime y prime 2, if you add them, you'll get x plus x prime, y plus y prime, and 4, which is outside the set.
Yes, sir.
Right.
We'll have to
So with
define
this,
additive inverse as x comma y comma minus 2 here. It's a question.
no, you just do it minus x
Yeah, minus x
minus y
minus
2
y
itself,
minus 2.
because when you add some, not minus 2, it is the third coordinate is 2 itself, because your inverse
Yes,
also
sir.
has to lie in the set.
Yeah.
And that
Yeah.
third coordinate is not changing. Like even if whether it is so if it as long as it is 2, if I do x y2 and minus x minus y2 and I add them, I'll get 0 0 2, which is the identity in this vector space.
X y comma 2. Yeah, got it, sir.
Yeah, 0 0 2
Sir,
is the identity, minus x minus y2 is the inverse, additive inverse. Yeah.
Sir, is isomorphism defined only for transformations or matrices also?
Isomorphism a, is a linear transformation between two vector spaces, which is bijective. So you have a map between two vector spaces, and you have to check three conditions, whether it is 1, 1, on 2, and a linear transformation. So your vector space could be the matrix, a set of matrices, or solution space of homogeneous equations, or polynomials of some degree, or whatever examples we had come up with and we have seen. or even the examples that we have not seen. It does not matter what the vector spaces are. As long as you're given two vector spaces and a map between them which satisfies certain properties, then it is called an isomorphism. Is that clear?
Yes,
Yes,
sir.
sir.
Yeah. Okay. So back to the question, does there exist an isomorphism between R2 and R3? Can I construct a map which is 1, 1 onto as well as a linear transformation?
So I think it is not on two. It is not on two, I think.
So you can,
Yeah,
are you
on
saying,
to yeah, on to will not be there.
okay, you're saying whatever map I construct, you can never make it onto.
Yes, sir.
Is it any map or any linear map cannot be onto? Or a linear transformation cannot be onto?
Sir, I'm taking a step back and trying to relate this onto feature
Yeah.
with the matrix being invertible or the determinant being non-zero. Am I thinking incorrectly?
Where are we have not talked
Sir,
about matrix yet. So
can we do this uh, x and so this R2, we take vectors from R2 which have
okay,
two coordinate and then make a third coordinate out of it with C1 times first coordinate plus C2 times second coordinate.
So like what I've concluded, like why we cannot look at it uh, that there does not exist an iformism for this particular
Mhm.
function is like because the like we can see that the dimension of the codomain is greater than the
True.
dimension of
That
this
is true. So
domain. Yeah.
the two inputs that I've got so far are f can never be onto, that is one guess. And the other thing that I've been told is you just define the map as x comma y comma some function of x and y, some c1x plus c2y or whatever. So, but will that be a bijective linear transformation? So
No.
let's forget about
Mm,
this
I'm not sure.
c1x plus c2y. So these are the two points that we want to take forward, right? Like f can never be onto is not a true statement. You can have a map from R2 to R3 which is onto, but that will not be linear. It cannot be linear transformation. In fact, there is a bijection from R2 to R3 also. This you can look up things like space filling curves and so on. This is way beyond the scope of this course. I'll just say that this is correct and can never be onto if f is linear. I'll just say this. Okay, this is correct, but this is not on. It is linear, but this is not on. So
Like
these are the
if
logical
is
conclusions.
if like f is not linear, like is it in our syllabus? I'm just asking, sir, to like it is possible.
What's your question? If it is
Like
not linear,
then how we conclude that it can be like mapped to onto and how we'll conclude it. I'm not.
you don't understand how there can be a map from R2 to R3 which is onto. Is that what your question is?
Yes, sir. If it
Yeah,
is
but
not
that is
linear.
that is hard. There are like very weird maps which uh, which can be
Like,
used to construct maps from interval to the whole plane and all that. So that's why I said that is beyond the scope of this course, and I'm not going to. So if you want to look it up, you can just Google it and you'll find enough
Okay.
resources about it.
Okay, sir. Okay.
But if I get an onto map, then I lose linearity. If I have linearity, then I lose ontoness. I cannot have both together. This is true. And that is why there does not exist. So the answer to this question is no. But intuitively, it does seem correct that onto maps should never be possible. But then how do I formalize it? Right? If I look at things like f of 1 comma 0, suppose it is x naught y naught, or let me call this x1 y1 z1. You want oh okay, over here, and this is x2 y2 z2. Suppose you have any linear map such that f of 1 0 and f of 0 1 are given like this. You can take your favorite numbers if you don't like working with symbols. But then you look at any f of x comma y. This is forced to be. So you know that this is f of x times 1 0 plus y times 0 1, right? I'm just writing xy as x times 1 0 plus y times 0 1. And using the linearity properties of the transformation, I'll get this is x of, let me call this, fine. This is okay. Hopefully this is not confusing. Here I've used the linearity properties to say that this is the same as x times f of 1 0 plus y times this thing. So this is x times x1 y1 z1 plus y times x2 y2 z. Right? Do you understand this computation?
Yes, sir.
Yes, sir. Sir, but like why
Yeah.
you used this standard basis thing like 1 0 and 0
I
1?
could use any basis, but
Okay.
standard basis is easier to communicate the idea. I'm saying that
Okay.
whatever f of xy is, that will be a linear combination of x1 y1 z1 and x2 y2 z2. But
Okay.
linear combination of two vectors in R3 will always just be a plane through the origin. So there will definitely be vectors not in this plane, right?
Yes.
So I can say that f of xy, irrespective of what xy is, this is in span of x1 y1 z1 and x2 y2 z. And what is the dimension of this span of x1 y1 z1 x2 y2 z2?
Two.
Should it always be 2?
It can be one for the
Uh,
So it,
yeah, less than 2.
so if since it is less than or equal to 2 and my ambient space, which is R3, which is the target space, that has dimension 3, there will definitely be vectors outside this span. And those can never be images of F, right?
Yes, sir.
Right. So this is the most general example of you just look at two linearly, like if you want to go even more generally, this 1001 I've just taken so that there it is easy to see. You can take any two linearly, like you can take any basis of R2, look at their images. Those things span a maximum of a two-dimensional space in a three-dimensional space. So you cannot cover all the vectors just by taking linear combinations of those. So that is why the answer to this question is no. So what is the next natural question? Does there exist a linear transformation, all of the same thing, f from R3 to R2? So here, let's just note that surjectivity fails. Surjectivity is onto, by the way. So does there exist a linear transformation from R3 to R2?
So I think injectivity will.
No. No,
Yeah,
sir.
that was sort of foreshadowed. So this is no, but injectivity fails. Or oneness fails. So here, what would be the way to go about formally proving it? You look at a basis again, which is say 100, 010, and 001. You look at the images of those bases. They are three vectors, right? And three vectors can never be linearly independent in R2. So they'll have some linear combination of each other. So I'll quickly sketch it. I won't go into the details. Suppose your F110 is V1. I'm just going to call it V1. I'm not going to call it X1, Y1, X2, Y2. This is a two coordinate thing. Just note that this is a two coordinate thing. This is V1, V2, V3. Suppose you have something like this. Then, okay, oneness I have not actually talked about when injectivity fails. We'll see that later. So V1, V2, V3 are linearly dependent in R2. So there exists C1, C2, C3 in R. What does linear dependence say? Not all zero, non-trivial ones. So such that C1, V1 plus C2, V2 plus C3, V3. This is equal to 0. Correct? This is happening in R2. Is this clear? Are things clear until this point?
Yes, sir.
Yeah. Now, if I take the f of no, you want these are linearly dependent. Let me take the alternative formulation, which is one of them can be written as a linear combination of the other two. So suppose I can write V1 as C2 V2 plus C3 V3. It could be V2 or V3 on this side as well. So what happens in this case is if f of 100 and f of C2010 plus C300. So using the properties of the linear transformation, you'll know that this is V1 and this is C2 times V2 plus C3 times V3. Correct? So you have f of something equal to f of something else, which contradicts injectivity. Is that fine? Or
Yes,
should I
sir.
go, should I clarify? Okay. If that is fine, then yeah. Otherwise, take a look at this. This is sort of self-explanatory. You cannot have 100 equal to 0 C2 C3, but f of 100 is the same as f of 0 C2 C3 because of the linear relation between V1, V2, and V3. The same is if V2 is equal to some linear combination of V1 and V3, or if V3 is a linear combination of V1 and V2. So in either case, what you have is that the dimension of the range space being lesser forces injectivity to fail, and the dimension of the range space being bigger forces surjectivity to fail, which is again intuitively clear because if you have larger dimension range space, there is no way you pick up all the elements. And if the range space is smaller, by smaller I just mean dimension thing. So you are bound to hit one guy twice or many guys twice. So there is no way you can uniquely assign one guy to another guy. So here the answer is injectivity fails if it is lesser, the dimension of the, and note that we are doing all of this only for Rn. We have not even talked about general vector spaces. But this does give you an idea that dimension plays a huge role in determining whether uh, an isomorphism exists from one space to another or not, right? So at least in Rn can be isomorphic to Rm if and only, sorry, only if m is equal to n. Now, is it if and only? The answer is yes. So fact is two vector spaces we end up with. For now, I'll say have an isomorphism between them. People also call it, they are isomorphic to each other, an isomorphism. If and only if dimension V is equal to dimension W. So, so here you saw that dimension can be an obstruction, but this fact says that it is the only obstruction. So if you make sure that your dimension of domain and codomain are the same, then you can have an isomorphism. And the emphasis is on can have. Of course, between vector spaces of the same dimension, I can have maps which are not isomorphisms. I'm saying that there exists at least one which is an isomorphism. If you take R2 to R2, this fact does not say that every linear transformation between R2 to R2 is an isomorphism. I could just take XY is, say, x comma 0. This is not surjective, for example. So, but what I am saying is, as long as you have VW, I can manufacture an F, or I can come up with an F, which is an isomorphism, as long as dimension of V is equal to dimension of W. So,
Sir, if I
we'll try
imagine
to.
the isomorphic function as something where there is no information that is lost, something which has no null space, would I be wrong?
Yes,
I
null space is related to injectivity. Null space just says that you are not uh, hitting multiples, but it does not say that you are covering everything. Surjectivity is not covered by the concept of null space, or it is called kernel in this case. So that we'll get to. So when you say, so this guy is the zero in the target vector space. If there is a non-zero element which maps to this, some information is lost. So this is what you're intuitively thinking, and you're
yeah,
correct
yeah.
that. Uh, but just avoiding this, saying that everything goes to, like, non-zero guys goes to non-zero guys, then information is not lost. But what is the guarantee that every guy is picked up, right? So
Oh,
surjectivity is not covered.
okay, yeah.
Right? So it is not just the zero space or who hits zero. So which actually naturally leads to this question, or this result that F from V to W is injective. Note that these are all linear transformations. So when I say F from V to W, I will not be always saying that V and W are vector spaces and F is a linear transformation between them. All of that is assumed from now on for this session. So is injective if and only if kernel of F is the zero subspace. So is there's only, I have not said what kernel is, right? Has kernel and range been covered in the previous session?
No, no, no.
No, sir.
Okay. Okay. If f of v is equal to 0 implies v is equal to 0. Let me just call it this. So the only vector that goes to 0, but f of 0 is equal to 0 is covered, right? This property of linear transformations that f of 0 is equal to 0.
Yes, sir.
Yeah, this I think has been covered. If you don't remember, you can just look at this. F of 0 plus 0 is equal to f of 0 plus f of 0. This is by the first property, but f of 0 plus 0 is just this. And then you use cancellation to get f of 0 is 0. So 0 is always mapped to 0 under a linear transformation. That's why translation maps will not be linear maps. But then injectivity happens if and only if I double f is if and only if v is the only guy that is mapped to sorry 0 is the only guy that is mapped to 0. So again, that diagram was probably good to push this. This always happens. But what about other guys? If this happens, then it is not injective. This is what this result says. I'll probe it in a bit. Let's take like a 2-minute break. I'll just get some water. See you at around 9293 something like that. Yeah, I think we can continue now. Where were we? Yeah, just a moment. Yeah, sorry, let's continue. Right. So injectivity is equivalent to having only one pre-image for 0. So this is what this result says. And this is true only for linear maps, of course. So if you look at non-linear maps, like f of x is equal to x square from R to R, this is not a linear map, right? F of x plus y is not the same as f of x plus f of y. X plus y the whole square is not x square plus y square. So this is not a linear map. And it's quite obvious why it's not a linear map. But what about, is this injective? Is this map F injective?
No.
Yeah. So f of 1 is the same as f of minus 1. So f is not injective. But it does satisfy the fact that f of x is equal to 0 implies x is equal to 0. The only pre-image of 0 is 0 itself. But still it is not injective. So the statement that has been written above, this is true only for linear transformations. So that's something to note. And that also shows the strength of linear transformations, right? So instead of checking for every point, does you choose any element in the codomain and then you look at how many pre-images it has, you should check that it doesn't have multiple of them. But if you have a linear structure, if you have a linear transformation between two vector spaces, all you need to do is check if 0 has multiple pre-images or not. It always has one pre-image, which is 0 itself on that domain. But does it have others? That solves injectivity problem for linear transformations. So the proof of this result I'll very quickly sketch. So suppose this is injective. So this is an if and only if statement, right? This part, you know that this is injective, and if this is a trivial part. If f of v is equal to 0, then this is actually f of 0, right? F of 0 is always has to be 0. But because of injectivity, two things cannot go to the same thing 0. So this implies that v is equal to 0. For the other part, which is the non-trivial part, if 0 has only one pre-image, then I have to show that v is injective. Sorry, f is injective. So I start out with a general statement: f of v1 is equal to f of v2. And I want to say that this happens only if v1 is equal to v2. And what does this imply? F of v1 minus f of v2 is 0. Because of linearity, this means that f of v1 minus v2 is equal to 0. So v1 minus v2 is an element which is mapped to 0. But the assumption is that 0 is the only element that is mapped to 0. So this forces v1 minus v2 is equal to 0, or v1 is equal to v2. So I started out with f of v1 is equal to f of v2, ended up with v1 is equal to v2. So this is exactly injective. So in other words, f is injective. So even if you don't follow all of the steps of the mathematical proof, what you need to know is, in order to check if a linear transformation is injective, all you need to see is what are the pre-images of 0. What are the elements in your V which are mapped to 0? If that is only 0, then you're done. So let us take maybe an example to see this more clearly. Right? I have a linear transformation from R2 to R2, which takes x comma y to, let's say, x minus y, y minus x. Is this a linear transformation? That is true. You can check that. But is this injective?
Excuse me, sir.
Yes.
Could you please show that above example? I missed the last part.
So this is not an example. This is a proof
Okay.
of the statement that injectivity is equivalent to having only one pre-image for 0.
Okay, sir. Got it.
Yeah.
Thank you, sir.
Do you want me to? Yeah. Okay. This is. Are your doubts clear?
Yes, sir.
Yeah. Okay. So how to apply that result is this example. This linear transformation, is this injective?
No.
Why is it not injective? So let us
Because there
use
can be
the,
some x minus y and y minus z, which is also equal to some other w minus v and w minus v. But it doesn't mean
yeah,
that x
but
and y will be w and v.
yeah, that is what you have to show. You have to give explicit examples for that, right? You can't say there can be, because what is the guarantee that there will be?
1 comma 1 and 3 comma 3.
Yes. So you have t of 1 comma 1 is equal to t of 3 comma 3. First of all, yeah, this is linear. Exercise P is linear. You have to check this. Only after that you can see that 1 comma 1, 3 comma 3, both of them go to 0 comma 0. But using this result, what you can do is you can just look at what are the vectors in R2, the domain, which are mapped to 0. So if t of xy is equal to 0, then you would have x minus y is equal to 0 and y minus x is equal to 0. Which means just that x has to be equal to y. And that is not unique. Like 0 is not the only element. Any vector of the form x comma x, t of x comma x is 0. So there is an entire line of vectors which are mapped to the 0 vector. So this is definitely not injective. And in this case, the function that I had chosen was easy. It was like x minus y, y minus x. But what about, let's say, example? I'll not give numbers because then I'll forget it at some point and that's a mess. So let's say 2x plus 3y, and what do I want? 6, 12. Now, just a moment. Yeah, in two-dimensional case, I can't really come up with different things here. It will do something. Yeah, is this injective or not? Is this immediate to see that this is injective or not injective?
Sir, I did not understand the previous example, sir.
Okay. In the previous example, your function is xy goes to x minus y, y minus x, right? I want to see if it is injective. The straightforward way to check it is come up with, so if your claim is that it is not injective, you have to come up with two vectors which map to the same vector, two different vectors which map to the same vector. That would contradict injectivity, yes?
Yes,
So the
sir.
candidate that was suggested was 1, 1 and 3, 3. So t of 1, 1 is the same as t of 3, 3, which is 0, 0. But what I'm saying is, in the case of linear mapping, you don't even need this other guy. If you just say t of 1, 1 is 0, if you have any vector, any non-zero vector which is mapped to 0, then you're done. Injectivity fails right there.
Okay. So like this
So
is
here,
this particular example is
yeah, so t is not injective. What about this? Is this injective?
No.
What is the
3 minus 2. 3 comma
yeah?
minus 2
So
would.
if you look at 3 minus 2, what is t of 3 minus 2? 0, 0. So there is a non-zero vector which is mapped to the 0 vector. So this is not injected, correct? But what if I changed it to, I'm taking only RNs, the domain and codomain that you have might be more complicated, like some plane in R3 going to R2, stuff like that. First of all, the primary check is that if you have your dimension of the domain greater than the dimension of the codomain, then it cannot be injected due to an argument that we had given earlier. But let's say 2x plus 3y and 2x plus 4y. Is this injective or not?
The 0 0 vector will only happen for 0 0.
Yeah, should be injected.
What is should be? It's either yes or
Because
it is no.
if we assign it to 0 0, then 2x cannot be 3y
Uh-huh.
and 4y both. Means 2x cannot be minus
So you would
3y
want
and also minus
2x is
4y.
equal to 3y and 2x is equal to 4y. Now, if you solve the system of equations, what will you get? 0, 0. So this is the moment where you have to connect it to the previous things that you have learned. So this is what? 2, 3, 2, 4, xy is 0, 0. This is this system of equations, yes? It's a homogeneous system of equations. So finding injectivity or establishing injectivity is like finding the null space of some matrix. Yes? So you want this matrix times xy. And any linear transformation is of this form. It's like ax plus by, cx plus dy, as long as it is R2 to R2. So somehow injectivity also comes down to the equation of solving a system of linear equations. And in this case, the determinant is non-zero. So the only solution is the zero solution. So do you see how all of the things are coming together? And even though we did not really uh, use system of equations to define injectivity or vector space or equivalence of vector space, but somehow they are all coming, uh, uh, they're appearing
So
in
like
multiple
finally, this
places.
particular example, I think I have understood because of this criteria. Like it has to be a unique zero trivial solution. Then only like
Yes,
this can
yes,
be treated as one to one.
yes. In general, if you have Rm to Rn, you will have an n cross m matrix that we will look at in the next few minutes. So it will come down to the solution of that. All of that will be clear when I discuss that. So in general here, I've just taken R2 to R2 specific examples, but this is what happens in the general case also, but with possibly different numbers. Okay.
Yeah, fine. Sir.
So this is isomorphism. And just like we looked at vector spaces and said that basis is a very important concept. Why? Because every vector can be expressed in as linear combinations of bases, right? So what is the role of basis in the context of linear transformations? This is what we'll see next. The guiding statement is that basis defines. So if I'm given a function, not necessarily a linear transformation, say t from v to w, think of t as just a function from a set v to set w. So what do I mean by defining this function. I have to give you the information about every element of V, like what is every element of V mapped to. But the strength of linear transformations is that they are a special class of maps where only the information on a basis is sufficient to determine where everything else is mapped to. Let's make that precise. So suppose V1, V2, Vn, and this is something that we've already seen actually. So in these examples, in this example in this one, for example, we saw that f of 1, 0 is something, f of 0, 1 is something, then the general f of xy is given in terms of the images of 1, 0 and 0, 1. Right? Similarly, even in this example, we had the images of basis vectors, like the standard basis vectors, and everything will be determined by this. This is not being used over here, but it is being used over here actually. In this example, it is being used very strongly. Now let's make it formal. This is, let's not go for ordered basis right now. Basis of V. So the basis of the domain. And then TV1, TV2. This is another convention that we don't write T bracket V1. Sometimes we just write TV1 without the brackets. Determines. What does that mean? So if I tell you what the images of any basis is, then you can get information about the image of any vector. Why is that? So given any V in V, there exists C1, Cn real numbers such that V is equal to C1, V1, Cn, Vn. And this representation is unique. So this is just because of the span condition of the basis. And uniqueness is because of the linear independence. But then what is T of V or TV? Using the linearity properties, this is just CTV1, C1 TV1, C2 TV2, and so on up to Cn TVn. This is just using two of the properties of the linear transformation. But I know what these vectors are, right? TV1, TV2, TVn. So as soon as I know the image of dimension of V many vectors, I know the entire map. Once again, this helps in things like data compression, where you just need to store the information about a whole map on an infinite set. You just need some finitely many numbers, and everything else is just a formula, right? Is this clear? How the image of a basis determines the entire linear transformation? Was that a yes or a no?
So I think I've understood. Yeah.
Yeah. Okay. So this linear structure seems to have many strengths, many of which we are using now. If I know what the basis elements go to, then I can determine the entire linear transformation. And I have a easier way to check for injectivity. Surjectivity is still the same thing for every element in the codomain. You have to produce an element. You have to come up with an element in the domain which is mapped to that element. That is not simplified, but it will be presented in a different way when we discuss the next topic. And this thing, the next thing that I will say is a vector space V is isomorphic to the standard vector space Rn. So N is, what do you think N is? Fill in the blank. What is the natural candidate?
Dimension.
So earlier I said that
Number of
if
columns.
dimension is not equal, so there's no number of columns over here because V is an arbitrary vector space. So it could be anything, right? It could be polynomials, it could be something like that. So there's no number of columns. So I'm saying V, given a vector space V, I can always find an isomorphism to Rn, where n is the dimension. Dimension is defined for any vector space. So how do you go about doing this? Is that uh, choose a basis. You can choose any basis. V1, V2, Vn. So the size of the basis has to be equal to the dimension, right? Choose a basis V1, V2, Vn of V, and then set PVI is equal to EI. EI is the standard ith coordinate vector, which is like 0 everywhere except the ith position where it is 1. And this is an element of Rn. And you can check that. So as soon as I say TVI is EI, the value of T on every vector is determined using the linearity property of the linear transformation. Right? So there is a way to extend this definition to all of V. And you can check that this is an isomorphism. So every vector space seems to be isomorphic to Rn. So why do we even work with different vector spaces, right? You can just work with Rn. Technically, yes, but for uh, convenience reasons, we still work with vector spaces because Rn will intuitively not make certain things clear. For example, how polynomials work, or how if you take some weird vector space, if you just equate it to Rn, then it's it, it's difficult to think about everything as just Rn. But technically, it is just Rn. So that's the next thing. And now this actually proves this fact also, modulo certain statement. This isomorphism is an equivalence relation. So equivalence relation is something that everyone knows or no? Do you guys know what an equivalence relation is?
Sir, I don't know.
Reflexive, reflexive, symmetric, transitive.
Oh,
I
yes.
think this
Yeah, yes,
must,
sir. Yeah, yes, sir. Sir,
yeah.
no, sir. Okay.
So if V is always isomorphic to V. If V is isomorphic to W, then W isomorphic to V. So this is true, right? Isomorphism is an equivalence relation, is what I'm saying. V is isomorphic to W, and W is isomorphic to, let's call it some, yeah, V1, V2, V3 implies, sorry, and implies V1 is isomorphic to V3. Yeah, so these things are easy to verify. So you can use all of these things together to say that V is isomorphic to W if and only if dimension of V is dimension of W. The earlier fact that we had stated can actually be proved uh, using this argument. Okay, so that's that about isomorphisms. And next, what we will do is in the big picture that I was saying earlier, we we look at objects, we look at examples, non-examples, constructing examples using subclasses or operations between objects, and then we define what is equivalence. And after this point is where you make a connection to existing things, or you look for interesting properties of these things. We have seen many interesting properties while we were doing equivalence and others as well, and we had connections, obvious connections to systems of equations. Gaussian elimination was used for determining linear independence and so on. But now is one of the more important points of the whole course, where we talk about matrix of a linear transformation. Let's take, for example, the earlier R2 to R2. What was it? 2x plus 3y and 2x plus 4y, I think. Even if it was not the thing earlier, let's take this. So if you look at R2 as the space of column vectors with two coordinates in real numbers, what I can write this vector 2x plus 3y, 2x plus 4y as 2x plus 3y and 2x plus. Earlier, had I written something wrong? No, it was correct. So I can write this as this, right? It's just a matrix times the vector. So this linear transformation is of the form A times this vector. What is A? We'll see. If you take another example, let's say xy goes to 2x comma 0. Is this also just a matrix multiplication? Can you write this as some matrix times xy for all x comma y? Let's keep it 2x 3y. Yeah. So what is this matrix?
2003.
2003 words. Right? So how did we come up with 2003? This we just saw the definition and we figured this out. And all linear transformations are typically written like ax plus by plus cz if you have R3, for example, R3 to R2, whatever. And you can form this matrix. So to every linear transformation, we can associate a matrix. But for Rn, this is maybe sort of obvious. But what about arbitrary vector spaces? How do I say what the matrix of a transformation is if I'm giving you some polynomial space? So to formalize this, what we look at is the following. Given any vector space, given, I'll just take an ordered basis. An ordered basis means it's not just a collection of dimension of the vector space, many vectors. It is an ordered collection. Order also matters. So this basis 1001 is different from 011. So the order in which you write them matters. So that's what I mean by ordered basis. Given an ordered basis v1, v2, vn of a vector space V, every vector can be written as some linear combination, some unique linear combination. You should know that this is a unique linear combination. Why? Right? This is fine. Written unique as this.
Yes.
Yeah. So every vector V can be written. So this set of real numbers C1 to Cn is said to be the coordinates of V. Now this vector space V could have been something which does not look like Rn as it is, but the coefficients with respect to some basis is always an n-tuple of real numbers. And that is what we call the coordinates of V. Okay, I'm not sure if this is covered in the professor's notes, but this is some standard terminology which makes sense, right? So in R2, you express every coordinate, every vector as two numbers. Like say, if I take the point 1, comma 2, you say the x coordinate is 1 and the y coordinate is 2. And why do you say that? Because this thing can be written as this 1, 0 plus 2 times 0, 1. And these are the standard coordinate vectors in the x and y direction. So this is your 0, 1, 0, and this is 0, 1. And every vector can be written as linear combinations of these two vectors uniquely in R2. And this is the same thing that we are making a little bit more abstract, that in a general vector space, given a basis, you can write uniquely. So if you take a different basis, the coordinates will be different, of course. Even in R2, if I take this and this as my basis, maybe some different color. If I take this and this as my basis, my 1, 2 will look different. My 1, 2 is somewhere over here, so it will be 2 times this plus some fraction times this. So it will not be the same, right? So coordinates are dependent on the basis, but given a basis, coordinates are unique. Now, why am I talking about coordinates is that what we actually did while trying to figure out the basis, going back to the example, trying to figure out what the matrix is, I looked at this guy, which was 2x plus 3y, 2x plus 4y. And look at what t of 1, 0 is. What is t of 1, 0? This is just 2, comma 2. What is t of 0, comma 1? This is 3, 4. And what did we write as the matrix of the representation? It is 2, 3, 2, 4. So let me write this over here. 2, 3, 2, 4. So what do you see? Do you observe something?
So like it is not unique.
What is not unique?
So the matrix like associated with the linear map. It is not.
I've not said what the matrix is, right? Yet. So in this case, we saw that it is multiplication by this matrix.
Okay.
So what do you see as the relation between the image of the basis vectors and this matrix?
Sir, it's the column of the matrix.
Yeah. So this is T of E1. This is T of E2. 2,
So they are
2
putting it column wise
and 3,
only.
4. Yeah. So it, in this example, at least, the columns of the what we call the matrix of the linear transformation is actually the image of the basis vectors, right? And what about the second example? We have 2x, 3y. What is t of 1, 0? It's 2, 0, which is C1, T of 0, 1. This is 0, 3, which is C2. Column 1, column 2, C1, C2. Right? So here also you see that the image of the basis vectors, we have taken the standard basis, are actually the columns of the matrix that we call the matrix associated to the linear transformation. So the most general construction is the following. Given a linear transformation, V to W and ordered basis. V1, V2, Vn of V, W1, Wm. So I'm taking a linear transformation from an n-dimensional space to an m-dimensional space, and not necessarily equal to m. We can associate a matrix to T as follows. So the steps to construct the matrix will be, you look at T V1.
So I only have a question, sir.
Yes.
Like we can associate a matrix to linear transformation. Whatever
Yes.
you will discuss, we'll discuss it. And
Uh-huh.
like we can say the converse of it. Like every matrix can also be associated with
Yes.
a linear
Yes.
transform. Okay.
That's a back and forth thing.
Okay, fine. Okay, sir.
So right now we are discussing how to construct matrix given a linear transformation and a pair of bases. So you look at the image of the first basis vector, V1. So now that is a vector where is TV1? What set does TV1 belong to? Could you repeat that? I didn't hear you.
That belongs to V.
V1 belongs to V. T of V1 belongs to W,
Oh, right.
right? So I can express this guy as, there is a reason why I'm doing it this way. You'll see that A11 W1 plus A12 W2 so on up to A1N Wn, right? Because TV1 is in W and W1 Wm, W1 up to Wm are a basis for W. So I can write any vector in W as uniquely as a linear combination of the Wi's. And I do the same procedure for every basis vector. I take every basis vector of the domain, look at its image, and express it as a linear combination of the basis on the codon. So if I do this, wait, what is this? This is 1, A, N, 2, W, 3, so on. A, N, M. This is what I wanted. M cross N is what I wanted. This is fine. Let's see, let's see. So I get a total of NM coefficients. Okay, I made a mistake, sorry. I will just rewrite this. Right. How do you write matrices? A11, A12, A21 is the thing, right? Yeah, yeah. This is the correct expression. 1, 2, 2, 2, M2, 1N, 2N, M. This is the correct expression. So what you have to do is take a basis of the domain, look at its images, and express those image vectors in terms of the basis which is given to you on the codomain. You will get mn many coefficients, and you arrange it in such a way that this is AM2. You arrange it in such a way that columns correspond to vectors on the domain. So the first column is the coefficients of TV1. The second column is of TV2. And the last column is that of TV2. Right? You have n many columns, n many rows. So m cross n. So this is an m cross n matrix. If it is a dimension n space to a dimension m space, then you have an m cross n matrix. This is one way to remember it. Now, let us see, instead of dealing with so many symbols, an example of the same. What was our map? What was it? 2x plus 3y, 2x plus 4y. Now, this was with the standard basis on both sides. We saw that the matrix. So, okay, with standard basis, look at SPD basis. You have T of 1, 0. This was, well, I'll just write it out as this. T of 0, 1 was 3 times. No, wait, what did I do? This was correct? No. T of 1, 0 was 2, 2. Yeah, 2, 2 is okay. And this was 3, 4, right? So these coefficients 2, 2, 3, and 4, these are the things that we are interested in, expressing the image of basis vectors with respect to the basis on the codomain. In this case, both bases are taken as 1, 0, 0, 1, the standard ordered basis. So what is the matrix? I'll take these two things, make it the first column. I'll take the other two things and make it the second column. Now, not with respect to standard basis. Suppose with respect to 1, 0, 1, 1 on both domain and codomain. So the basis that I'm using is different. Right? So what is the algorithm? I look at what T of 1, 0 is. This is my first basis vector. What is T of 1, 0? It's 2, 2. Now, how do I write 2, 2 as a linear combination of the given basis?
The sum A times 1 0 plus B times 1 1.
Yeah, what are the AB? It's easy to see.
0 and 2.
0, yeah.
Yeah. So in this case, it is just 0 and 2. And what do I have to calculate? What is the second thing that I have to calculate? T of what?
1 comma 1.
Okay, so since the basis that I've chosen on both domain and codomain is 1, 0, 1, 1, I have to evaluate T of 1, 1, which is what? It was 2x plus 3y, 2x plus 4y, so it's 5, 6. So how would I write it as 1, 0 plus 1, 1? So this has to be 6 because that is the only contribution that I'm getting. But then I'll get 6, so I'll have to put a minus 1. Correct? So the matrix representation with respect to this basis is 0, 2, minus 1, 6. There are some notations like m of t with respect to beta, gamma, where beta and gamma are the basis. You check the prof's lectures to see what is the convention or notation that he uses. But this is the matrix representation of this linear transformation with respect to these bases. So there's kind of a lot going on. You need a linear transformation and what basis you're working with. You have to evaluate the linear transformation on the given basis on the domain and express it as a linear combination on the basis given on the codomain. So in both of these examples, we have taken the same base on the domain and the codomain. It can so happen that you have a different basis on the domain and different basis on the codomain. It becomes more, the calculation becomes a little bit more difficult. But all of this, at least algorithmically, makes sense, right? So what is the point of getting this matrix? So at least over here, we did see that every vector was of the form 2, 2, 3, 2, 4, xy. What does this matrix even give you? Is it just some 4 numbers? No. So this is also matrix your linear transformation can also be expressed as uh, matrix multiplication with respect to this matrix also. But how? So if I give you a vector, let's say 2, 1, what is T of 2, 1? 2x plus 3y, 2x plus 4y. What is the direct evaluation of T of 2, 1 gives me what?
7 comma 8.
7, 8, right? Yeah, 7, 8. But then what are the coordinates of 2, 1 with respect to the given basis? So you remember what coordinates are with respect to 1, 0, 1, 1. Coordinates are the coefficients which express this vector. So I can write 2, 1 as 1 times 1, 0 plus 1 times 1, 1, right? So the coordinates of 2, 1 are 1, 1. This is the, let me just write it in a column vector. This is the coordinate. So this one and this one, these are the coordinates in that order because we are taking ordered basis. But in this case, it is both coordinates are the same, so there's no confusion. But in general, you have to write it in the order given for the basis. Right? So 1, 1 are the coordinates of 2, 1. Now look at what happens when you multiply the matrix of the transformation with respect to this basis. 1, 1. What is the answer?
Minus 1, 8.
Right. But what is minus 1, 8? So what is the vector which has coordinates minus 1, 8? So if I do minus 1 times 1, 0 plus 8 times 1, 1, what do I get?
7 comma 8.
And what is this?
The function.
Right. So the matrix representation or the matrix of the linear transformation with respect to given basis actually takes coordinates of vectors to coordinates of vectors in the given basis. So now you might still think that it is unnecessarily complicated. Like I always have a representation with respect to the standard basis, which is easy to read. Why do I have to go through so many translations? Like you find the coordinates in some basis, look at its image, look at its coordinates, manufacture the matrix representation, and then if you want to check the value for any vector, you have to again write that vector in terms of you have to find the coordinates of that vector, and then you have to do a matrix multiplication to get coordinates, and then recover it using the given basis. So it seems like too many steps, right? Why do we do this? Why do we go through so much pain? So one example which might make it more uh, clear or to show you the strength of this thing, consider this transformation x minus y, y minus x. This was the thing that we did earlier. Right? So what is the matrix representation of T with respect to the standard basis?
One zero zero one.
It's not 1001. What is T of 01? T of 10?
Oh, 0000. No, sorry.
No.
It will be 1 comma minus 1. 1 comma
And
1.
this is minus 1,
Minus 1 comma 1.
1. Right? You have 1, minus 1, minus 1, 1. So the image of the first basis vector will be the first column, and the image of the second basis vector will be the second column. So yeah, this is the matrix representation. But there are places where linear transformations are some sort of recursive process. Like I want to keep doing this. So the input is a vector. I want to keep applying this vector over and over again, this transformation over and over again. If I do what is called as t square of v, which is nothing but t of tv. Since we are in the R2 to R2, if I take a vector in R2, I operate t, I get another vector in R2, I can operate t on that again to get t of v and t of v and so on. Like I can look at this t of v, and I can keep doing this. And there are recursive processes which depend on transformations like this. So if I look at this matrix representation, it becomes, if I look at a vector v, it goes to, let me call this matrix A so that I can uh, use it better. It becomes A times v. This is a matrix multiplication. And then this becomes A squared, which is A times v. And this becomes A cube v, and so on. The number of times you want to apply the linear transformation on the signal vector or the given vector is nothing but the number of times you have to multiply A with itself. But then if you try to multiply A for a general matrix, maybe for this matrix it is easy, but for a general matrix it might not be very easy to calculate the nth power of a matrix, right? But then you look at what the representation of T with respect to the basis. Let me see what I want. I want uh, 1 minus 1 and 1, 1. So what is the representation or what is a matrix? Let me call it matrix of T with respect to this basis. To see that I need to do this first. What is T of 1 minus 1? It's nothing but 2 minus 2, right? And this is 2 times 1 minus 1 plus 0 times 1. What do I need to do next? I need to look at what t of 1, 1 is. But that
0
is
comma 0.
just 0, 0. And this I can write as 0 times 1 minus 1 plus 0 times 1 comma 1. So what is the matrix in this basis? It is 2, 0, 0, 0. Right? Now, if this is your A, then you can see that A to the power n is 2 to the power n 0, 0, 0. So if you use this matrix to represent your linear transformation, you can sort of get an order of convergence. In this case, it doesn't even converge. This diverges, right? 2 to the power n diverges as n becomes larger. So this matrix representation clearly tells me that if I keep applying the signal on the same vector, it blows up. The amplitude or whatever the thing is, it blows up. But that is not very clear from this because computing a to the n in general may not be easy. So this goes into diagonalizability and all that. This is not part of the course, but there are certain bases with respect to which your matrix representation is simpler. And that is why we go into the theory of how to represent a linear transformation with respect to a basis which is not necessarily standard also. So I will end this session with this comment that what we have to summarize what we have discussed so far is linear transformations from V to W. This is in one-to-one correspondence with matrices of size. I don't know if you call it size or order or what. Dimension W cross dimension V. So this one-to-one correspondence is always with respect to basis B1, or let me just call it BV and BW on V and W respectively. So if I'm given a specific basis on V and a specific basis on W, a linear transformation is nothing but a matrix. That's what this says. So the rest of the content of week 6 explores this parallel even further. So you have already seen what null space of a matrix is and what column space of a matrix is. So under this correspondence, what does null space of a matrix mean for the linear transformation that that matrix corresponds to? Or given a linear transformation, uh, what is the quantity that is captured by null space and column space? All of this is the rest of the content for week 6 that will be taken up in the next sessions. And yeah, earlier we were I was saying that we do the reverse construction as well, as in going from linear transformation to a matrix is there, and then how do you go from a matrix to a linear transformation? That was briefly explained over here. If I'm given a matrix and a basis for the domain and codomain, you write the coordinates of any vector, and then you do the matrix multiplication and get the coordinates of the target vector. This is how you define the linear transformation. I've not explicitly written it down, but it was already mentioned. So this is the height sort of, which says that linear trans. Just a minute, I'll listen to you in a bit. Linear transformations and matrices are the same. In the background, there is this condition that you have to specify the basis. But once you are given two bases, then a linear transformation is just nothing but a matrix. So that is one of the parallels which is very important. And henceforth, whatever notion that you encounter for a linear transformation, you should ideally ask the question, okay, what is the corresponding notion for matrices? Or if you see something in matrices, then you should ask what is the corresponding notion for linear transformations of vector spaces. So all that is more general stuff. The more particular things that are part of the course content we'll be taking up in the next session.
Sir, can you scroll up a bit?
And yeah,
A bit
how
more.
much are there?
Yeah, this part. Yeah, sir, I'm getting lost where we discuss matrix of T with respect to basis 1 minus 1 and 1 comma 1. What exactly are we trying to do here?
Yeah, that was the algorithm that was said earlier is you look at this basis 1 minus 1 1 1.
Where did this
How do
basis
you
come
construct
from?
them?
Wait, this
So
one.
I had written it down earlier because I knew that this would work well, but there is a way to come up with this also. I have not told you how to come up with this nice basis with respect to which your matrix is nice. There is a way to do it. There are eigenvalues, eigenvectors, and so on. So, but that is not part of the course. But I'm saying that there is uh, in this, I've not told you how to come up with the nice basis, but I'm saying that there are bases which give you advantages over standard bases. This was just an example to demonstrate that.
And what are we trying to achieve?
So matrix of T with respect to the standard basis was 1 minus 1 minus 1 1, right? So if you recursively apply the transformation T on a given vector, that is like multiplying by the matrix over and over again, which is at the nth recursion of applying the transformation on the vector, you'll get a to the n times v,
Yeah.
which may not be easy to compute in general in term for an arbitrary n. So you cannot readily get the data on whether uh, the vector, or this is more relevant to signals theory and all that. So will the signal blow up or will it converge to zero and so on? That is not readily visible over here. But with respect to the new basis, 1 minus 1, 1, 1, how do you construct the matrix of that? You look at the image of the basis vectors, which is T of 1 minus 1 and T of 1, 1, and express them as linear combinations of the given basis again, which again I've done over here. And then you get the matrix with respect to it using the coefficients 2, 0, first column, 0, 0, second column. So that is your matrix. And the transformation is again matrix multiplication by this matrix, but for the different coordinates. Like in order to compute the T of V, what you have to do is look at coordinates of V and then do A of those coordinates. Suppose V1 and V2 were their coordinates with respect to the new basis. Then T of V is nothing but matrix multiplication of A with V1, V2. So in this case, you can see that A to the n is 2 to the n, 0, 0, 0, right?
Yes.
This is a diagonal, like a scalar diagonal matrix, not a scalar matrix. So scalar matrix multiplications are easy. So diagonal matrix, so this becomes at the nth step, you have 2 to the n. So as you keep applying the same transformation on your given signal, whatever this quantity corresponds to, amplitude or whatever, it blows up. So this is not a transformation that would converge. All of these are vague terms which are not relevant to the course, but I hope you are at least getting the idea that by using this particular basis, we have inferred something which may not have been possible for for this matrix. So this is a nice basis which gives you a nicer representation of nicer matrix representation. Like different bases, different choices of bases give you different representations, matrix representations. So which one is the best one, or which one is the best that you can hope for? There is theory in that direction. I was just giving this example to motivate or to illustrate the fact that this is not a purely theoretical, futile attempt of just abstract stuff, but this actually has some meaning.
Why would we want to apply the same transformation recursively till the infinity?
So this is once again not something that I am very aware of too, but there are these things which the signal goes through the same transformation over and over again. Uh, you can look up signal theory for that. I am not very familiar with it, but I know that this is a thing.
Okay, interesting.
Excuse me, sir.
Even if it is something like, okay, just a minute, just to add on to that, it might not even be signals. It's like sometimes when you talk about image processing also, when you store your image data as some grayscale image data as numbers, which is a gradient between say 0 and 255, and then you
Hmm.
write it as a matrix. So one way to blur an image is by matrix multiplication. And if you want to blur the image over and over again, you'll be multiplying this matrix of
Ah,
data with the
yeah,
same
yeah,
thing
yeah.
over and over again, right? So you want to know the rate of convergence of that, or order of convergence of that. So this might be something which is probably more well defined as an
Yeah.
as an illustration. Okay. Is that fine?
Yeah.
Yeah. Okay. Other doubts? If you don't have any doubts, feel free to leave.
So like we have used the coordinates like for the transformation with respect to this basis vectors, and by using that coordinates of
Mm-hmm.
different bases with respect to different bases as expressed previously, and
Uh-huh.
you have come to a conclusion where you have like used those coordinates and put it into a matrix, if I'm
Yes.
not.
Yes.
So like I want to like a little more understanding of it, because uh, like if we are if any transformation is used like with respect to the basis
So
to the
linear
domain of the domain.
transformation,
Yeah.
linear transformations. What do I mean by this is a matrix representation? Linear transformation is matrix multiplication. This is what it says. In what way? As you saw that this thing, p of xy is 2x plus 3y, 2x plus 4y. This I just saw that t of, if I write it as column vectors, this was what? 2, 2, 3, 4, xy. But what about matrix representation with respect to other bases? So, of course, this is not the same as which was the other basis that we calculated 0, 1, minus 1, 2, 6. 0, minus 1, 2, 6 was it? Yeah. This is not true, right? This is not true because I'm saying that this is a matrix representation for this linear transformation itself. But what is its meaning is that this xy is not your canonical coordinates. So here your x tilde, y tilde is with respect to some other basis. So your vector is x tilde times v1 plus y tilde times v2. Where v1, v2 is your given ordered basis. If this happens, then p of v is equal to, in this case, it will be what? Minus y tilde times v1. So I've taken v1 and v2 for both uh, domain and codomain. In general, it will not be that. 2x tilde plus 6y tilde times v2. So the only change is that you don't use the standard coordinate. So when you have matrix representation with respect to different coordinates, you have a different basis. You have to express your vector with respect to that basis, and you will get the coordinates also with respect to that basis.
Okay, sir. So one more thing, sir. Like this,
Yeah.
understood. Like even if like the basis is not given, because
Mhm.
like you have chosen the standard basis on standard ordered basis,
Right.
but
Hmm.
if it is like not given in a
Okay.
sense like when you provide some other basis in R2 only in any dimension, then
Okay.
if it is not given, then we have to choose the standard basis or like
So
um,
that depends on you are free to, if there is no uh, basis given to you in the question,
yes.
and if it is said, say, compute the matrix representation. If it is said that compute the matrix representation and no basis is specified, it is always assumed to be standard ordered basis.
Okay.
Yeah. And if there is something that has to be computed with respect to a particular basis, then that will be specified in the question. I'm assuming that your question is only about exam questions, right?
Yes. And sir,
Yeah.
like we have done two examples where we have taken for the same transformation function which is given, we have taken two
Yes.
different bases, and
Yes.
we have like concluded two different matrices also. So we can also say that this
Right.
is not unique, though the matrix.
Of course. Yeah. 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 It will. It is highly non-unique, as in, given any basis
Okay.
on the domain, given any basis on the codomain, you will get a different. Yeah. There might be some same matrix representations, but uh, most of the time it will be not the same. It will be, in this case, you have seen that it is 0, 1, 0 minus 1, 2, 6, and 2, 3, 2, 4. But there are some properties which will stay the same, like trace and determinant and so on.
Okay.
Determinant in the case of square matrices. That we will see later.
Okay.
You will
Fine.
discuss what similarity of matrices are and equivalence of matrices are, and then what does it mean for linear transformations and so on. So that is actually the subject of maybe next week or the week after. Yeah, please go ahead. You don't need to raise it. Just ask the question. But we have a wrap up soon. Yes. Are there questions?
No, no,
Oh
you're not.
no, I don't think so. I'll be stopping streaming now. But yeah.